Hello. Next we have the first oral of the session. The title of the paper is Sample Efficient Reinforcement Learning with Stochastic Ensemble Value Expansion. The authors are Jacob Buckman, Danny Jar-Hafner, George Tucker, Eugene Brevdo, and Hong-Lak Lee. It'll be presented by Jacob Buckman.
Thank you. Good afternoon, everybody. On behalf of my collaborators at Google Brain, I'm proud to present our work on sample efficient reinforcement learning with stochastic ensemble value expansion. Stochastic ensemble value expansion, which we abbreviate as STEVE, is an approach to deep reinforcement learning that merges model-based and model-free techniques. We use ensembles of neural networks to maintain uncertainty estimates for both the Q function and dynamics model, and use model-based reinforcement learning only when we are confident in the predictions of our dynamics model. We evaluate on a variety of continuous control tasks and find that STEVE is able to match or surpass the performance of model-free approaches, even in complex environments. First, some background. Our algorithm is based on DDPG, so we have a neural network Q function approximator parameterized by theta to predict the expected return for a given state action pair, as well as a policy function pi parameterized by phi to predict the action which maximizes Q in any given state. The Q function is learned in the standard way. When interacting with the environment, we maintain a replay buffer of transitions. So each transition contains a state S, the action A taken in that state, and the resulting reward R and next state S prime. We update our Q function by minimizing the squared error between our initial guess based on the state and action and our updated guess incorporating future information. This is known as the TD target. Our work also builds upon model-based reinforcement learning. In model-based RL, we learn a dynamics model, which predicts how the environment will respond when we take an action. In our case, we learn both a transition function, T, and a reward function, R, each of which are, again, neural network function approximators. There's a large amount of literature on model-based reinforcement learning with many strategies for using this dynamics model to accelerate learning. In our work, we focus specifically on using the model to improve our target. Specifically, we build on recent work on model value expansion. So the idea of how that works is, starting from the next state, S prime, shown here in green, we use our policy to predict actions, and then use our dynamics model to predict rewards and future states, essentially rolling out our model into the future. This gives rise to a new target, which is simply an n-step Q-learning target on our rollout. We refer to this as the NVE target, which is subscripted by some rollout horizon h, corresponding to the number of steps of rollout. In this case, we have h equals 3. Comparing this to our TD target, it's easy to see why this might help. The discount factor applied to the Q function for the NVE target is gamma raised to the power of h plus 1, in contrast to the TD target, which is just gamma. The contraction rate of the Q function is equal to this discount factor, so if the reward and state predictions are accurate, then we expect that the extra discounting will lead to faster convergence. However, dynamics models are not without their own issues. The error of the learned model puts an upper bound on the performance of the learned policy, because even a policy that performs perfectly in an incorrect model of the environment could have poor performance in the real environment. Additionally, this is somewhat likely to happen because the policy learner is in some sense adversarial to the model, in that it will actively search out model errors if those model errors correspond to the reward being overestimated. And finally, even if our model is very accurate, multiple steps of model rollout could cause initially small errors to compound into large errors that then cause the first two issues to arise. So, going back to our comparison of these two targets, we can see that there are many opportunities for model errors to affect the NVE target, but none in the case of the TD target, which of course makes sense because standard TD learning is model-free. So, hopefully that gives everyone a good sense of the factors at play here. Model-based approaches can improve the sample efficiency of DQN, but using a learned model comes with many issues and can hamper performance. In model value expansion, this trade-off is clear. More steps of rollout increases the contraction factor, but introduces opportunities for model error. To see this in action, here's a simple value approximation task in a tabular environment. For this environment, we know the true value function for each state, so we can compute the error in closed form after each update. This green curve shows how regular, model-free TD learning gradually converges to the correct Q function, taking about 20,000 time steps. In red, we now see what happens if we do model value expansion instead, using an oracle dynamics model, one that perfectly matches the dynamics of the true environment. We can see it converges far more quickly. However, what if we don't have access to a perfect dynamics model? What if we only have access to a noisy one? This dotted red line shows what happens. Even with a small amount of noise, the model-based approach not only performs worse than the model-free, but actually completely fails to converge at all. Our work on Steve is motivated by a desire to fix this issue. We've seen that each step of model value expansion comes with a trade-off of sorts. We want to compute a target, T-Steve, that reliably balances this trade-off to have a lower overall error than either the TD target or the MVE target. The intuition for how we want to do this is we compute many MVE targets with different rollout horizons and choose a length of rollout that doesn't make significant model errors. In order to figure out what length to choose, we estimate our uncertainty and ignore high uncertainty targets. Our approach assumes deterministic environments and policies, and we leave stochastic environments and policies for future work. So these MVE targets at many different horizons we refer to as candidate targets. First, notice that the TD target is actually equivalent to the MVE target with a rollout horizon of 0. We can then get our other candidate targets by extending this for each horizon up to some maximum, rolling out one step at a time. Written as equations, these simply correspond to the various n-step targets. Now, in order to compare the goodness of these targets, we need to additionally maintain uncertainty estimates. We use the Bootstrap Ensemble technique, which involves replacing each neural network with an ensemble of neural networks. For example, in this particular instance, we replace our transition functions with an ensemble of size 2. The two transitions functions are represented here as blue and cyan. We initialize each member of each ensemble randomly and train them on different independently sampled mini-batches at each update. We can then sample many different combinations of these functions to get different estimates of the MVE target. So let's say we wanted to compute the 2-horizon MVE target and its uncertainty. We would start by sampling a neural network from each of our ensembles, and then just compute the target as regular. In this case, we sampled dark green, blue T, and orange R. If our ensemble sizes are small, in this case we only have 2 of each, we could exhaustively enumerate the combinations of ensemble members, but in general, what we want to do is resample several more times and get many different estimated values of our 2-horizon target. This procedure is where Steve gets its name. We maintain various ensembles and do value expansion by stochastically selecting a new subset each time. Once we've taken many samples, we can use the mean as our target, and the variance gives us an estimate of our uncertainty. Repeating this procedure for each horizon length gives us h+1 candidate targets and their corresponding uncertainties. We want to merge the targets into a single target with minimum expected error. We first decompose the expected error into the bias and variance terms, and in this work we ignore the bias and focus only on minimizing the variance component. If we assume that the candidate targets are independent, it's well known that the minimum variance estimator of several independent estimators can be computed via constrained optimization, resulting in inverse variance weighting. As an aside, we can also include the covariance terms, but computing the target then involves taking a matrix inverse, so it's much slower. We find that it doesn't make a significant difference in performance, so we don't do it in practice. So essentially, as you can see here, our final target for T-Steve is a weighted average of our candidate targets, where the weight of each horizon length is proportional to the inverse of the variance of the predictions at that horizon length. Here's a visualization that should give you some intuition about why and how Steve works. The y-axis of each of these figures represents several updates to the model, maybe multiple samples from a mini-batch or multiple sequential updates. The x-axis corresponds to the rollout horizon used by that respective target. The darker a square is, the more weight is being given to that horizon length. The TD target assigns all of its weight to the 0 horizon rollout at every time step. The MVE target always rolls out all the way, assigning all of its weight to the maximum horizon length. We also could consider simple methods, such as taking the mean across all different horizon lengths, or decaying the weight with TD lambda. These result in slightly more interesting plots, but note that all of these approaches are still consistent across samples. In contrast, Steve produces this interesting patchwork behavior, as it flexibly adjusts its rollout horizon on an example-by-example basis. This additional flexibility is where Steve derives his power. To see this in action, let's bring back that toy problem that we saw earlier. Here, we add on the Steve curves in blue. As you can see, the solid blue line, representing Steve with a perfect world model, converges almost as fast as MVE does. However, the dotted blue line, representing Steve with a noisy dynamics model, now still converges, and in fact, even still converges faster than regular Q-learning. We also evaluate on a number of larger scale continuous control tasks. Note that we are now reporting reward, not loss, so higher is now better. The blue line here is again Steve, while the red and green lines are our model-based baseline, model value expansion, and our model-free baseline, DDPG, respectively. We see that Steve matches or outperforms the baseline on every task. Interestingly, this gap is larger on the more difficult tasks, such as humanoid V1, even though the dynamics of these environments are much more difficult to model. To further investigate whether our algorithm is robust to model errors, we took the most complex environment and ran several versions of Steve with various maximum rollout horizons, visible here as various blue lines, with the darker lines corresponding to longer horizons. We can see that as we increase the rollout horizon, the sample efficiency improves, without the performance degrading. Finally, we also include here in pink a version of Steve that takes into account the covariance. As you can see, the performance is not significantly better or worse, but it was much slower to run, so we used it only for this curve. Speaking of time, computing the Steve target at each time step does take significantly longer than the regular TD target, up to 5 times more. We ran the experiments comparing the wall clock time of these algorithms to determine whether the increased sample efficiency granted by Steve made up for the slower per update speed. We found that Steve either matched or surpassed baselines in terms of wall clock time on tasks that we investigated. To summarize, we introduced Steve, an uncertainty-aware reinforcement learning algorithm. Our technique for merging model-based and model-free approaches leads to high performance and sample-efficient learning. All our code is available online, open source, and please come check out our poster number 167 if you would like to learn more. Thank you.
We have time for a question, if you'd like to come to the microphone. David?
Great.
You're good.
So the key difference is that Dyna, you're actually doing all of your training in the sort of modeled environment itself, in the simulated environment. And then you're doing one step, you're sort of mixing in one new step of environment interaction per cycle, whereas with these approaches, every single update is computed using both some information from a real transition and some information from a simulated transition.
Are there other questions? So I was wondering, what happens in stochastic environments? Obviously, this won't quite work out of the box, I guess. What do you see as being needed to apply it?
Yeah, so in stochastic environments, our estimates of uncertainty end up merging both the sort of epistemic knowledge-based uncertainty and the aleatoric uncertainty fundamental to the environment. You could wind up with a sort of a rollout horizon that has a large amount of variance in its value, but that's because you had to roll a die on your way there, and that's where the variance comes from. But really, we should be confident in that target because we have high confidence in our knowledge of the distribution of values at that point. So it would actually only require a slight change in the formulation with regarding to how we do that uncertainty approximation, and you would need to take at least 2 samples of each ensemble the same way. But it would be not that significant of a change, but is left for future work.
Okay. Anything else? Yes. Can we turn on the microphones?
Almost none for these tasks. All the sort of simulators are simply feed-forward neural networks of 3 layers that take in the state representation. We do low-dimensional proprioceptive inputs for this, not from pixels, but it just takes in that vector of proprioceptive inputs and the action used, and passes it through feed-forward layers and returns another vector, another state vector. So almost no structure is included in this. Adding an additional structure would likely help, and that's a direction that we'd like to explore in the future.
All right, great. Thank you. Let's thank the speaker again.